Hi all and welcome back. This stream is just coming on, just getting started, so that was really great. I think, that's always the way. Technical stuff, if you've been watching my live streams, then you'll know that I'm sometimes late and technical things sometimes go wrong. But yeah, exactly. I'm really excited for you next year, Lewis, because you're going to spend that time, really kind of honing your skills on the channel, and it's really great to work with you. I hope you've enjoyed this. I felt like for me that half an hour to get prepared for the next one was a little bit short, but you know what I had to do was kind of rush upstairs and feed my my baby a bottle before she sleeps. So that's something that my wife needs help with just before we get on. So I hope it's all been really useful for you. I'll be here for another half an hour. I've got a few more things. I'm really sorry, and I really need to apologise to one of the chaps who did a super chat. I've never taught the moles section. Now I'm assuming this is something to do with if you've got a number of moles and you need to use Avogadro's constant to get a number of actual molecules, a number of actual particles in there, and from that maybe to a mass as well in physics. Okay, it's the type of thing that comes up in chemistry. I know they use that. I did mention that in the last one in the gas laws. I know they use that number of moles and R, which is called the molecular gas constant, as the constant in the ideal gas section. So maybe that is what you're talking about there. I've just noticed that you're looking at what I wasn't expecting you to look at. I was expecting you to be looking at me directly. But as we've just discovered, technical things. Right, so we're going to jump back in, and I've got a few more things for you. I've written them all down. I've got, and was asked for, resonance, circular motion, SHM, and emission spectra, and then a really quick bit about diffraction gratings. But I think that just before I do that, I'll talk about, Lewis mentioned it, don't panic, you're well prepared. Go in there and show it your best shot, all right, and really think about that. Now, there are some really hard questions, and one of the questions at the end of this feed I'm going to go back to, and it's from yesterday's hardest exam questions feed, and we kind of struggled to work it out. But today it's been really good. People have been commenting how they solved this question, how they actually do this, how they, how can you figure that out, what a strange context it is about this game show in SHM. So that's really good to see people actually engaging with it and not thinking straight away like, oh, that was a hard question. It's so hard that even a teacher and examiner still gets tripped up on it. All right, so don't be shy about getting tripped up on it. Just think about picking up those marks. Think about every single mark just matters that bit, and you can get enough marks to get your target grade in this exam. Right, let's jump into the visualizer, and I'll go through those things. So what's coming? Resonance, circular motion, SHM, and emission spectra, and diffraction grating. So I'm going to play the one with the jump scare. So here it comes. Oh no, I've played the wrong one. Alright, okay, so this one is resonance. Now I know that actually Lewis talked about it briefly as well. I just want, it was asked for, so why not? Okay, so resonance, remember this little explanation. Driving frequency matches the natural frequency. There is a maximum energy transfer, so there's a rapid increase in amplitude. So that is the definition of resonance. What happens is a driving frequency is actually at the same frequency as a natural frequency, which is the frequency of something as it would just vibrate if it were just set vibrating. Okay, and when those two frequencies match, then it's the most efficient energy transfer, if you like. So that is why there's a really rapid increase in amplitude, and that's what you do on a swing, right? You kick your legs forward and backwards at the natural frequency of the swing, and that energy transfer gradually increases the amplitude, quite rapidly actually, increases the amplitude of the swing, and off it goes. So often they like to think about doing an experiment with this, and what you would do is I should put frequency, but we know they're inverse one another anyway, so similar idea, is you increase the frequency of your driving frequency, and you look out for this little spike, okay, and you'd have a sharp peak, okay, a sharp peak. That's very important. If you're asked about to sketch a graph for resonance or something, the examiners are looking for a nice sharp peak, because there's a kind of exact frequency, an F0, a natural frequency at which the resonance will occur the most, right? And before and after that, you don't get anywhere near as high amplitude. So you need to have a rapid fall off of the graph there. All right. So also following on from that, damping is something that we can do to stop resonance. Right now, it doesn't necessarily, damping doesn't stop resonance. What it does is it removes energy from the system. So if you like, we're not changing the frequency, we're changing the energy transfer. We're taking the energy out of the system. And really these ones have a graph that looks like this. So instead of being a normal SHM graph, you have this sudden and rapid kind of decrease in amplitude of the graph. Now this is not a good sketch. I'm going to talk about sketching SHM graphs in a moment when you sketch sine curves, because a sketch doesn't mean without a ruler. It means that you don't need all the numbers on there. You just need some key kind of bits of data, right? Okay. And what I wanted to do with this is just illustrate the fact that damping follows exponential decay rules. So we can do all the same stuff that you do with exponential decay with damping. Okay, so you can find out a kind of damping constant, which is just like any other exponential decay. And they really like in A Level Physics, they really like to ask you to work with exponentials because it challenges you. Alright, moving on to circular motion. And however I think about circular motion, this is the equation that pops up into my head first. So this is the definition of a centripetal force. Okay, so mv squared over r, mass times velocity squared over r, which is the radius of the circle. If you think about that, most questions either come through this in some way. Okay, most questions either involve calculating this or using this to do a derivation. So I've got a couple of derivations with this equation, actually, to this equation and from this equation. So in this case, another definition of V in the formula sheet is omega r, where omega is what's called the angular velocity, or the angular frequency, sometimes called as well. So that is the number of rads per second, basically, omega. And that's r as well. So we can put that into the same equation instead of V, and we end up with this expression here. So often you look at it and you have to work out a centripetal force. And remember to get that word in there, centripetal force, which is always towards center of a circle. Then this is two ways that you can do it. Maybe they've given you a time period and you need to get omega before you go ahead and do this. Maybe they've given you an r, but they haven't given you a v, and they've given you a mass, okay, but they haven't given you a v, in which case you need to do something like this. Now this all comes from Newton's second law as well, and it's this kind of idea of a resultant force. Okay, so another thing that might be there in a explain question would be a resultant force. Okay, Newton's second law, F equals ma, or resultant force is mass times acceleration, and the definition of angular or circular acceleration is v squared over r. Now you can see, hopefully, that goes into the equation, and you get back to this circular motion equation here. So just to kind of bring this all together, if you know the time period, you know an angular velocity. If you know an angular velocity, you know a time period, because they just inverse one another by 2 pi. Right, now 2 pi is the number of radians in a complete circle. Most of you will have no issues with that at all. It's equivalent to 360 degrees. And I just want to say, make sure that you have your calculator set up in radians mode. Lewis mentioned that, okay, that kind of thing, getting yourself ready. And Adam Smith actually had a really good tip, and he said he's got a sticker on his calculator that reminds him to make sure he checks whether it's degs or radians. Right, now I don't know whether exam rules that's specifically allowed, and you don't want to get caught out, but even if, Adam, if you peeled off your sticker that said check degs and radians, then at least they'd have a kind of sticky mark there which would remind you, oh yeah, that's the thing I always do. It's about making those habits, isn't it? So before you go into the exam, make sure that your calculator's nice and set up, okay, and you're not going to have any issues with that. Alright, that's a good tip from Lewis earlier on. And now, circular motion also follows all the rules for SHM. So the things I'm going to go through in a minute for SHM also apply to circular motion, and vice versa. If it's SHM, you can use one of the circular motion graphs as well. So SHM, simple harmonic motion, okay, is defined by this point here. F is minus k delta x, which is actually Hooke's law, but it's got something added to it, which is the minus. And the minus implies towards. Right, so what does need to be the case for SHM is a force towards an equilibrium position, and that force must be proportional to the distance from that equilibrium position. Right, now it turns out that actually the spring constant is very useful for working that out, because if we've got a mass on a spring, well, it is literally the Hooke's law constant, which defines the time period of the oscillation. And I'll talk about those two equations for oscillation just after I've done this. The other condition for SHM is it's got to have a fixed time period, right? So there are often questions like this: define SHM, and you bang down these two things and explain, right? Towards an equilibrium position and proportional to its distance from it. You could also say the acceleration is proportional to towards the equilibrium position and proportional to its distance from it. Now you have three equations normally in Edexcel you certainly do, which define x, v, and a for a oscillation, right, for a simple harmonic oscillator. Now here they are in this little section here. So you can see we're just talking about, so omega comes up in this as well, as does this 2 pi f, which is just exactly the same equation as t equals 2 pi over omega, but just sub f for t, and you know t is 1 over f. Okay, so it's that same idea. Okay, the relationship between time period, omega, and frequency is the same idea. They just inverse one another by a constant. Okay, so yeah, there it's all written out. I don't know why I really need to write it out again. Okay, so anyway, I'm going to go back to these ones here. This is the displacement equation. This is the velocity equation. This is the acceleration equation. Right now, if you do maths, then you'll be familiar with this. Okay, but notice, okay, cos, sine, and cos again, right? Or minus cos, in fact, in this case, right? So when we're thinking of the graphs, and often they like you to sketch or compare some graphs, okay, then the x versus t graph, the displacement time graph for the oscillation, is a cos shape of graph. Now that makes sense. If we were starting something oscillating, okay, maybe the first thing we do is we raise it to its maximum position, its amplitude. That would be the amplitude. Maximum position there. Then we'd drop it and it would go down. The acceleration would be proportional to the distance from it. No acceleration as it went through the point there, okay, and then maximum acceleration again when it was furthest away, but again towards that equilibrium position, and it would just keep on going, doing that simple harmonic oscillation throughout time, unless we damped it, unless energy came out of the system, right? Now, okay, this v versus t graph, the speed time graph, the velocity time graph, is actually the first derivation of this graph here. And if you derive cos, you get minus sine, right? So, but we can think about it in terms of that oscillator. So we had maximum displacement at the start, okay, it means we had 0 speed at the start. We had, when it goes through the equilibrium position, we have a maximum but negative speed because it's going down through the equilibrium position. Then, okay, it's going back up, but the force is towards the equilibrium position, and it goes through the center, through the equilibrium position at its maximum velocity here, and then again back to 0 velocity back at the top again to start the whole cycle once more. Now again, if we want to get to an acceleration time graph, then again we use the differentiation to get there. So if you differentiate a minus sine graph, you get a minus cos graph. So the acceleration at the start is, it's right at the very top, so it's maximum negative acceleration. And if you get that as it goes, it's not going through the equilibrium position there. Yeah, it's going through the equilibrium position there, so it's its maximum velocity, maximum negative, okay, but there's no acceleration. And then when it's furthest away, it's maximum positive acceleration. Okay, so it's furthest away, maximum positive acceleration, and then through the equilibrium position again, maximum speed but no acceleration, and then back to the start again. So really, when you look at these equations given to you in the formula sheet, you can imagine those graphs. Now I wanted to talk about sketching those graphs, didn't I? Okay, so what I wanted to say to you is I've stacked them, so you can see I've stacked them, so I can think about these points as being vertically above one another. Right, so I can think about what's going on here, what's going on here, what's going on here. Right, now I can think to myself maximum gradient here, so maximum negative for the velocity time graph. Okay, stationary point there, so 0 on the acceleration time graph. Okay, and we can do that for all of the different parts. That's a really important skill in A Level Physics, actually linking your graphs. And what I suggest is sketch them on top of each other, and you'll be able to look down the graph. So here, look, stationary point, so 0 gradient, so on the velocity time graph, 0. Maximum gradient on the velocity time graph, so stationary point on the acceleration time graph, right? The other thing is that we said that it had to have a constant time period, right? So before actually doing the curve, I just put my ruler on and I did 4 equal points so that I could do a really quick sketch of a sine curve with 4 equal points. Okay, I hope that helps. Oh yeah, the equations for the different things. There's two types of simple harmonic oscillator, which are mass spring systems, which have the equation time periods is 2 pi root m over k, and a pendulum is a simple harmonic oscillator as well. Okay, T is 2 pi root L over G. So the only thing that affects a mass spring system is the mass and the stiffness. The only things that affect the pendulum is the length and gravitational field strength. So you need to take that into account. The only change we can make to a pendulum would be the length, or taking it to a different planet, basically. All right, that's that. Now, where did that come from? And I just thought I'd add this as a little aside. These are just normal displacement time graph, velocity time graph, and acceleration time graphs, right? So again, we can use what we know about calculus, differentiate x with respect to t, and you get the velocity time graph. So increasing gradient means increasing velocity. Differentiate v with respect to t, then you get an acceleration time graph, okay, or a little equation if you like for an acceleration. In other words, constant and positive acceleration. Now the same backwards, the area underneath an acceleration time graph is the velocity, or the average velocity. So if we integrate a with respect to t, then we get back to a velocity time graph. And same here, if we integrate v with respect to t, then we get back to the displacement, right? The total displacement is the area underneath a velocity time graph. So it's a really neat way to remember how the different graphs are related to each other. If you don't do calculus, you don't do further maths or maths, then that probably will go over your head. But just think about this: gradient, gradient, area, area. Okay? All right. Next thing was emission spectra. So let's talk about that briefly. And I think that's the last bit. We'll have a little look at the chat afterwards, and then I'm going to tell you what's coming up for your next set of exams as well. But I just want to talk briefly about this. And I've got two questions from my kind of hardest questions that I wondered that didn't print out, and so I didn't look at it, and one also that everyone's been talking about today, because it's one of those wiggy questions that's going to trip you up because it's got a crazy in a physics exam. Why would you give a context about a game show? I mean, it's just ugh. Okay, so emission spectra are when electrons are falling down the energy levels, right, and they're giving out photons. So let's talk about all the possible energy level changes of this little diagram here that I've sketched. It's not accurate, okay, it looks like what I kind of remember. A hydrogen atom, right, could be this lot. Okay, I'm not going to do them all. But there's loads of different options for energy level changes which give out photons. Okay, so this change in energy is proportional to the frequency of the photon, right? Now, if this graph here, normally they put wavelength this end, so increasing frequency this direction, okay, then you have all these as emission lines. So what this would look like would be dark backgrounds, and it's very hard to draw. So they draw emission and absorption spectra the same. It's hard to draw without giving you like a coloured insert, and it's not biology, we don't want to be printing coloured inserts. So this would be a black background with some white kind of lines. Right, now, as I said, this is really hard to draw, but I'll just quickly do it to make a point. Okay, these colours, they would correspond to the frequency, and remember that frequency is what defines the colour of light. Okay, does that make sense? So that's the emission spectrum, because there's all the possible energy level changes that from an atom, right? And they would emit, therefore it's possible to emit these different coloured lines. Just really quickly, then a lot of people get confused because the top one is zero energy and the lowest energy level, the ground state, is negative energy. So it's about where we measure from. If you can imagine measuring something, if you imagine measuring someone's height from the ceiling, right? Let's do that quickly. Let's do short person and tall person from the ceiling. And if we called this one 0, okay, and we measured the height with reference to the 0, to the ceiling, then this height might be minus 0.8 meters, and this height might be minus 1.2 meters, right? Now, it's odd because we've got a kind of higher but negative length for the shorter person, but notice this is a smaller number than this one. So the taller person still has a higher height no matter where we measure from. Okay, so that sometimes trips people up. Don't forget also that when we use E equals HF, we convert into SI units. So 13.6 EV becomes 13.6 times 1.6 times 10 to the minus 19 joules. Yeah, and that is the energy in joules. Okay, so I'm not going to calculate that, but make sure that you convert into SI. If you've got a non-SI unit, you can just imagine it like a little formula. So this is 13.6 times E times 1 volt, because the energy, EV is defined, 1 EV is defined as the energy given to an electron when it's accelerated through a 1 volt field. Now absorption spectra is the same, but what's happening when atoms absorb photons is electrons are being promoted up the energy levels. So just imagine kind of a set of all the different possible fixed energy level changes for this atom that I've sketched out here. Well, okay, each one of these would correspond to a different frequency of absorption. So what you'd see is all of the colours, okay, but you'd see these black lines whereby those photons were missing. So we're never just shining on one kind of colour of light, okay, we're shining all different colours of light. A white continuous spectrum is what you'd see there, but we'd be missing these certain frequencies of light because those are the frequencies that have been absorbed by the atom. I hope that makes sense. I just wanted to say one more thing about this. Oh yeah, about explaining. Get these words into your explaining, right? Get the word discrete when you're explaining quantum, okay, or fixed energy levels. Okay, there's only a certain place, only a certain amount of energy that an electron can have when it is fixed inside the atom. And talk about discrete energy level changes. Okay, in this case it's a positive change, they're being promoted up the energy levels. In this case they're coming down and they're giving out that energy. So really I always think, well, maybe E equals HF should be written like this, delta E equals HF. I don't often see it like that, but that reminds us that it's an energy level change that we're talking about, rather than just a fixed, just an amount of energy. About 5 more minutes that I want to do, although I will chat for a bit longer if you guys got questions, but not too much longer. Diffraction grating was the last thing that I wanted to talk about. So if you imagine the laser light coming towards a diffraction grating, okay, now you've got to imagine all of these diffractions overlapping from each of the different points. We'd only ever really ask you to draw that for 2 points. Okay, so Young's double slits would be just something like this. And you get these points of maximum and minimum, and you need to do this carefully with a compass. Okay, because where they are, where the peak meets peak, trough meets trough, you get lines of maximum along here, maximum, 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 or in other words, bright fringes. And but where a peak meets a trough, okay, so these are peak meets peak or trough meets trough everywhere along these lines. But then where a peak meets a trough, also in line, you get destructive interference, okay, and therefore you get these zeros. You get no light at all or no wave at all, no energy transfer along those points. So that's a really quick sketch. I mean, there's loads of really good videos where this is done carefully. I've got one as well. But I also want to talk about there's a phase difference. Now phase difference is measured in angles, okay, so I'm going to put in rads, brackets, and then there's a path difference which is measured in meters. Okay, so there's 2 ways to talk about this. Okay, now at these points here, this is where our screen is, this is where our wall that we're projecting this on, okay, each of these points have a phase difference of 0, okay, because they are points of constructive interference, peak meets peak, slash trough meets trough. Okay, so these are our bright spots, or bright fringes, sometimes called when it's a linear diffraction pattern. And in between that, you've got a pi phase difference, right? But also, this central one has 0 path difference. But this first order maxima has 1 lambda path difference. Okay, so it's gone 1 full wavelength further, so it arrives a full phase difference later. Okay, a full cycle later. And this one here has 2 lambda path difference. So it's still got a phase difference of 0, but it's got a path difference of 2 lambda. And I think that's really important to get that in there. Now the rest of this experiment I've gone through on all the experiments from A Level Physics, from Edexcel A Level Physics, so I'm going to leave that one there. I'm going to jump into the chat and I'm going to come back to tackle 2 of these kind of questions that people asked me about from my previous live feed. So let's have a little look at the chat if there's anything useful that I can give you. I hope this has been really useful to you guys. Here's the, well, let's do the music one. There's some sarcasm going on, I can see. Yeah, path difference is n lambda, I like that, that's good. Modal dispersion and material dispersion after. I'm sorry, Dan, I don't know much about that because I've not ever taught that, I'll be honest with you. So I'm really sorry to not be able to help you there. Yes, Mariam, yeah, it's a good idea to do a little group chat, maybe by the different exam boards, talk about what's going next. Yeah, it's, look, again, it's not different exam boards, it's just different, it's just things that are useful. My G, the finest driller. Okay, good stuff. Alright, I think you're going to do really, really well, guys. E fields, promote that electron, demote that electron. Yeah. Yeah, so there's the electrons feel the electrostatic force, don't they, between the positive nucleus and them, and that's where that energy is from. And rather than energy shells, let's call them energy levels, because they're not necessarily as discrete as just kind of the 2AA pattern that you're used to from chemistry. Based on this diagram, these electrons are moving down from outside the atom. No, well, the electrons outside the atom could have theoretically an infinite energy. They could have loads and loads and loads of energy, right? So we only need to talk about, with a very top band, we call that the valence band, when that's a kind of a free electron now. Okay, and that's, somebody asked the question about how do thermistors and LDRs. Well, it's how many free electrons there are. It's how many electrons are right up there in the top band, the valence band, therefore available to kind of conduct electricity or heat. Shots fired at biology, yeah. How many of you do all 3 sciences? How many of you do maths and physics? Yeah, I've talked about fasting quite a lot, guys. Be iftar soon, so that's great. Make sure you get lots of carbs in you tonight and tomorrow morning, because it's the afternoon exam, isn't it? A Level Physics in the afternoon, guys. I mean, it's not good enough from the QCA, to be honest, to schedule it like that. Yeah, it's all calculus, basically. This is the class whiz, the FX991EX, right? It built on the FX85 GT Plus. You know, it has a lot of the strengths of that, but it really is taking that a lot further. And bit of calculator geek in there for you. Right, I'm going to stop now. Thanks for the SHM, no problems. I'm going to stop and just have a look at some of the questions now, okay? I've got to try to set up the split screen transition. It looks really professional, yeah. We'll chat about the setup and how I do that after Lewis, yeah, alright. Okay, so let's go back into the visualizer and talk about this one. It's a moments question, and what else is it? It's an SHM question, so let's talk about that. Okay, so this is a moments question sent to me by one of the viewers, and the issue with this was, now maybe you can find out, but it's not actually that they couldn't do it, but they get a different answer when rounded to 3 significant figures than the mark scheme gives us. So let's just chat for it, because they can ask some pretty tricky moments questions, I think, right? So you got, when you recognise moments, okay, the first thing to do is to recognise clockwise and anti-clockwise, right? So this, the weight of the uniform meter ruler is providing a moment in this direction, which is clockwise, and the Newton meter is providing a moment in the anti-clockwise direction. So this is what this person's done, and they've just made one of them negative. They've gone straight from kind of clockwise moments equals anti-clockwise moments to just the sum of the moments, if I call one of them negative, equals 0, and that's absolutely fine. And they've worked in centimetres throughout this, which, okay, will kind of confuse me at first. Maybe I thought that was what they were doing wrong, but it's actually fine to do that because we can do that. I also like this skill. Can you see this? And Lewis talked about this in his live feed. Okay, he's worked something out here. He's worked out the weight of the ruler, and he's stored it in his calculator as A. So he's used that kind of alpha function, the memory function, to store that so it retains the full significant figures, because he's obviously conscious of this idea that you round to different significant figures, you don't get the mark. Okay, so that's absolutely fine. It's all worked out. Basically, just the weight is balanced by this Newton meter, and you need to determine the mass of the ruler. So you need to go everything, rearrange for m, and then you get, it should really say the mass of the ruler, but it would get the mark because it's got 0.161 kilograms, right? Then how can you check the ruler is horizontal? Use a spirit level. Okay, that's absolutely fine. You could use a set square and a plumb line, but probably that's the sort of most straightforward one. And then it's told that a 0.5 kilogram mass is added to this mark on the ruler, and that means you've got to look very carefully again and figure out the perpendicular distance from the pivot for that, which you can see in all the working that they've done here, and then write a new balancing equation, okay, basically with 2 clockwise forces, 2 clockwise moments, okay, minus the anti-clockwise moments, and x being F, the force that we want to work out on the Newton meter, and summed all that round and got 4.20 newtons. And the mark scheme answer is this. Now, I've gone through this a couple of times, checking the significant figures. I think they've done a premature approximation, so I think that they've, somewhere in here, they've done a premature approximation. Now, I'd always trust maths over a mark scheme. So if you're stressing out why is mine not quite close enough, and you've checked everything, then trust your maths, okay? Trust that you've gone through it a few times and you can do it. Okay, then the last thing, a uniform ruler of greater mass than 1 part, will you describe how you could alter the apparatus so the router is horizontal once more. So this is probably about moving the pivot towards the centre of mass. Okay, and then it says explain the reasoning, and this will decrease the moment. I would probably state which one it would decrease. Okay, this would decrease the clockwise moment, just to cover yourself in there. Okay, maybe state the principle of moments once more, maybe do a little louder as well to double cover yourself, that you're going to get both marks. I like this question because it's really clear where the marks are. There's one for describing how you could alter it, and one for explaining how you could alter it. Right, there we go. Okay, now this was the question that we were talking about yesterday, SHM question, which was doing our heading. Okay, it's about this television game show. Okay, now, right. This illustrates a point for me. They've given you a context which has nothing to do with physics. Nobody is sitting watching a game show thinking about SHM. The people who designed this probably didn't think about SHM when they were designing this game show barrier, right? And basically you have to get underneath the barrier, okay, just like Mario basically. Right, the barrier has a vertical height of 0.7 and moves up and down with simple harmonic motion. Okay, so they've given you lots of detail. You've got to think to yourself, the first one is just state, it's an easy question, the conditions that must be met for an object to have simple harmonic motion, and that's what I've just talked about in the previous one, towards a equilibrium position proportional to the distance from it, is the force, and a constant time period. And then, okay, you have to work out a contestant requires at least 0.6 meters high to get under the barrier. They've given you the time period in there, and they've told you about the bottom edge of the barrier is initially in contact with the ground vertical height of 2.3. Right, so this is the nuisance of it. Okay, so there's loads of kind of different information. There's 3 meters given there as being the vertical height of this whole mechanism, and there's a completely pointless bit of information. There's 2.3 there, but that's not the amplitude. So your first thing is to figure out where on this is the equilibrium position. So just consider the bottom of the barrier going up and down, and its maximum height is 2.3. Its equilibrium position must be halfway between that. So x0, I've called that equilibrium position 1.15. Now they have to get to a maximum, they have to get under it, they need 0.6 meters. So basically we're trying to work out a time at a displacement of 0.6 meters. But don't forget, and this is one thing that I forgot yesterday, don't forget that it needs to be, you're working out time, the maximum time they need to get under the barrier, it needs to be from when it's at 0.6 meters back to when it's at 0.6 meters. So you need to avoid using the time for this bottom part of the oscillation. So in other words, it's like a minus cos graph, okay? And if we think about up being positive, which we would, okay, then we use a minus cos graph. It would confuse you. It's really, it's going to be the x displacement is going to be a cos graph, okay, just like what we were talking about briefly a little while ago. And therefore, that's one of those equations from your formula sheet. Okay, there's the displacement graph, sine graph, and again the minus cos graph for acceleration. But we want this one, but we're talking about the negative section, the bottom section here, so we might as well just treat it as a minus cos graph. Okay, so this is a tricky question, but think about picking up the marks, right? If you're going to pick up the marks, then make sure that you do what you can do. You've been given a time period, you've figured out an equation with omega in it, so make sure that you convert clearly to a omega, okay, radians per second. That will get you a mark. This as well, show that you're using this equation, and to an examiner, use of doesn't mean writing it down, recognizing the right equation, it means subbing some numbers in. So even if those numbers aren't 100% correct, if you've gone ahead and put some numbers in, then you're going to pick up the use of mark. So actually, as far as I got, and I'll tell you why I didn't get the right answer, which is a bit embarrassing really, and that's left to Adam's point there. I'd have got 2 out of the 5 marks for sure by working out working out a omega and by using this equation. So that is one of the most important things to remember in that exam tomorrow. Start solving the problem. If you can't completely solve every problem, get some way towards solving it. That will pick you up some marks on the way towards the end of the paper. And then you have to figure out what that distance is from the equilibrium position. So it's not 0.6 we want to use, it's 0.55, which is the difference from the equilibrium position. Plug that into this equation here, okay, x being that, a being the amplitude 1.15, rearrange for omega t, do the inverse cos, and here's where I went wrong. I got 43.99. Any guesses where I went wrong? Somebody probably already guessed. Well, I didn't have it set up in radians, so make sure that your calculator is set up for whatever you're going to use in that exam. And if you're using 2 pi rather than 360, then it needs to be set up in radians. So by changing to radians, I got 0.77. That seemed really, really small. Okay, so then it was clear what we'd done is we'd calculated this time here from the bottom to 0.6. Now that's not the time we want. We want the time for the contestant to get under the barrier, which is the time from 0.6 right to the very top and back down to 0.6. So we have to actually deduct 2 times the time from the time period, and therefore it's 2.96 seconds, which is the time, the maximum time the contestant has to get under the barrier. Why do they ask you that rather than just asking you to figure that out? Then I don't know. It would have been a far more interesting question, I think, if it had been about some actual physics rather than a game show. But the context is there just to distinguish between the very, very highest level people and the kind of not quite 100% highest level people. So don't get upset about it. Just think, even in the really, really hard questions, you can pick up some marks. Okay, do some work in, show use of equations, put some numbers in, do the calculation as far as you can, and you will pick up some marks. Okay, I am going to kind of drop this feed just now. It's been an absolute pleasure chatting to you. Okay, I just want to talk to you about next week. Well, okay, I'm not going to be here quite as much over the next week, but I'm going to do a live feed again on Wednesday. So if you've got questions that you want for that, leave them in the comments for this video. Okay, things that you want to go in for paper 2. I'll maybe just, what I'll maybe do is just pop up on Tuesday and say, how'd your exam go, chaps and chapettes? Let me know if there's anything you want us to go through on the live feed. I'm hoping, Lewis, you fancy doing this again for next time and for paper 3 as well. I'm hoping it's been useful to you. If you've got suggestions on how it'd be more useful or not so useful, then do let us know. It's been an absolute pleasure to spend the time with you. Okay, you're going to be absolutely fine tomorrow. Take confidence into that exam. Before I go, I'll just have a quick look at the chat as well. So here's the musical intro for you. I think have I even done the jump scare one? Maybe I'll have to do the jump scare one just before we do. Just as a treat for you all. Please sit my exam for me. Sorry. Yeah, also I've got full A Level Edexcel A Level exam playlist. So paper 1 exam playlist is a good thing to go through, so do that. I mentioned that also Science Shorts has a really good playlist for all paper 1s. He's been really working hard to put out playlists for paper 1, so go over there and use them. But don't just watch them without thinking about it. Think about how he's solving the problems in front of us. Don't think about the papers that just gone. People talking about M3 paper. If it's done, it's done. Just leave it now. Yeah, momentum is pretty straightforward. I went over momentum in a playlist before the AS exams. So there was a live playlist before the AS exams where one of the things I talked through with momentum. Discord chat place for people, that's really good. Glad you love my beard, bud. Yeah, okay, so that's me. Jump scare 1, then I'm going to just give you a little wave, see if there's anything else. Are you ready? Just turn the volume down if you want. I think I've gone through all of that that I've planned to go through today. I like somebody mentioned, look at the background. Look at Lewis's, oh no, my camera doesn't work face there. That's so awesome. All right, Lewis, it's been a real pleasure. I hope that was useful for you. Let's chat more about using live feeds in the future. Tonight, just the little things. Maybe today and tomorrow, don't overstress it now. This is not going to be the time where you're trying to understand something that you've not understood for 2 years. Okay, so don't focus on that. Just focus on some nice light memory work. Okay, maybe take your equation sheet, take them all back to base units, maybe annotate an equation sheet from memory, that type of thing. Okay, just look over those little key bits that you think might be the difference between a mark or not a mark next time. Okay, review like easy explain questions, okay, or define questions. Look through your textbook and revision guide, look for those definitions and make sure you give out those kind of the definitions in the kind of exam board chat. Okay, remember, as we've said to you a few times, that there is only kind of some questions are designed for only the very top tiny 2.5% of people. Okay, so not all students are meant to get those things there. C grade students are meant to get 2 out of the 5 marks for that question, for example. A grade students are meant to get all the way, but only deduct 1 T, for example, and get 4 out of the 5 marks. Okay, so don't stress out about that. They're there to discriminate between C grades, A grades, and A star grades. Alright, just pick up the questions that you can. Look through my hardest questions in A Level Physics playlist as well, or live feed, because one thing I do there is I talk through Bloom's taxonomy for all the command words. Right, that's me. Good night. You don't need luck for tomorrow because you've been preparing for 2 years for this, okay, and you're ready. So it's not going to be good luck, okay? It's just go in there and do your best.